All right, hello everybody. Welcome. We are going to dig into a problem on equivalence classes here. So here we go. Let x be the set of integers, positive integers, from 1 to 14. Define a relation r on x by x is related to r if and only if 7 divides y squared minus x squared. The question is here, show that first off r is an equivalence relation, and then second, find its equivalence classes. Okay, so here we go. So now, first off, we should remind ourselves what is an equivalence relation. What's the definition? And if you're going to do any proofs, definitions are an absolute must. You have to memorize them. Now, so what does it mean to be an equivalence relation? Should I give you a sec? Can you remember? A relation is an equivalence relation if it is reflexive, symmetric, and transitive. Okay, 3 definitions, and you have to know the definitions of those 3 things if you have any hope of doing this. Okay, so first off, let's show it is R is reflexive. Okay, so what does it mean to be reflexive? Reflexive means that for any x in the underlying set, xx is in R, or another way to say that is x is related to itself. So we pick x, any x we want to be in the underlying set. Oops, I should be a little bit careful there. I've called the set capital X. So how about I use a different letter there? Let's just call it, oh, no, I've done that over here too in the question. So little x there, big X there. So we'll try to separate little x and big X. So let little x be an element of big X. So it is a number from 1 to 14. Then what happens? Is it true that x is related to x? Well, x is related to x, so let's reread this phrase here, replacing the y with another x. X is related to x if and only if 7 divides x squared minus x squared. Well, what's x squared minus x squared? X squared minus x squared, well, that's 0, regardless of what x is, right? Does 7 divide 0? Yeah, that's 7 times 0, right? 7 divides 0. Thus, 7 divides x squared minus x squared, and so x is related to x. Thus, R is reflexive. Great. 1/3 of the way there on the equivalence relation. Number 2, we need to show R is symmetric. What does it mean to be symmetric? Again, can you remember the definition? The definition is absolutely critical. Definition of being symmetric is that if x is related to y, then y is related to x. Okay? So I need 2 variables in my set. So I'll pick a lowercase x and y, both in the set x. And I'm proving an if statement. If x is related to y, then y is related to x. And just like in every proof, we assume the if. Assume the if part there, if x is related to y. So we assume x is related to y. Okay? Now what I need to show to be symmetric is that y is related to x. Well, what does it mean that x is related to y? All we know is the definition. The definition of that is that 7 divides y squared minus x squared. Or in other words, that is, let's just write it down here, there exists a k, definition of divisibility divides in z such that 7k is equal to y squared minus x squared. Now what do I want to show? I want to show somehow that y must be related to x. So, and you can write this if you want to. You could write, it remains to show that y is related to x, that is, 7 divides x squared minus y squared, slightly different. Or in other words, that is, there exists some m, so that 7 times m is x squared minus y squared. That's the same thing we just wrote, but switching the x and y around. But wait a minute. If 7k is y squared minus x squared. How do I switch y squared minus x squared to x squared minus y squared? I just negate it. And so if all I have to do is negate the right-hand side to switch the order, all I have to do is negate. And so maybe I'll just write this. Let's multiply both sides by -1. I'll show every step here. On the right side now, the right side actually becomes x squared minus y squared. Well, what do I do on the left? Well, I want to show that 7 divides this thing, so I want the 7 there. 7 times an integer. What's the integer going to be? -k. Bring the negative inside the brackets. And since k was an integer, -k is an integer. And what I have then is 7 divides x squared minus y squared. And therefore, x is y. Almost wrote the same thing again. Y is related to x, and we have, and maybe one more implies R is symmetric. Okay, so there you go. I've shown R is reflexive and symmetric. Hey everybody, let's take a break from the example for a sec. The example I'm doing here is really just a single example, and there are literally infinitely more problems you can run into on a discrete math exam. And odds are good you'll run into problems you've never seen before and be expected to apply what you know to solving them. But if you don't understand the content, you have no hope. So if you're taking a university, if you're a student taking a university discrete math course, and you're serious about not just getting a good grade, of course, yes, getting a good grade, but if you're serious about understanding the content, then go ahead and click the first link in the description down below and book a free call with me. Now, back to the example. Now, one more. Do you remember what it was? R is transitive. Now, what does transitive mean? You remember that? It means that if x is related to y and y is related to z, then x must be related to z. Okay? Same idea, same structure of a proof. I have 3 letters now, x, y, and z, so let's pick 3 arbitrary elements. Let x, y, and z be elements of capital X. And remember what I just said. It's an if. If x is related to y, and y is related to z, oh, so I assume the if. Always the same thing. Assume the if. Assume that x is related to y, and in this case, the if is an and statement, right? Assume both. If x is related to y, assume x is related to y, and y is related to z. Well, that is, I can write that out a different way. Another way of saying that is y squared, 7 divides y squared minus x squared, and 7 divides z squared minus y squared. Now make sure you can see where that came from. That's an important skill to be able to do here. All right, so what do I have here? I have 7 divides y squared minus x squared, and I have 7 divides z squared minus y squared. Now what do I want to show? And maybe I'll write this out. You don't have to. This is not absolutely necessary, but it's not a bad thing to do, especially when you get stuck in a proof like this. You're not sure what to write next. You can go ahead and just write, tell the reader what you're going to do. It remains to show that what? Well, I've got x is related to y and y is related to z. I need to show that x is related to z. That is what? Well, what would be the definition of that? Z squared, oops, again, 7 divides z squared minus x squared. So z squared minus x squared is what I'm interested in. Okay, well, how do I get that? How do I get a z squared minus x squared from those two? Well, look at this. Z squared minus x squared is actually equal to z squared minus y squared plus y squared minus x squared. Right? The y squareds actually cancel out there. And so what do we have? Z squared minus x squared, the thing I'm interested in, is a multiple of 7 plus another multiple of 7. Oh, well, if I take a multiple of 7 and a multiple of 7, and I add them together, what do I get? Another multiple of 7. Thus, 7 divides, z squared minus x squared, which therefore means that x is related to z. And again, one more conclusion, R is transitive. Okay, now you could say it here. It wouldn't be a bad idea maybe to say a little bit more there, so maybe I'll do that. Let's just insert a little bit here, extra here. Again, you want to make sure that you're always showing all the work you could possibly need to, right? We're looking to get all the details out here. But this is true, and so since 7 divides z squared minus y squared, and 7 divides y squared minus x squared, we have, there you go, 7 divides z squared minus x squared. Okay, a multiple of 7 plus another multiple of 7 equals a multiple of 7. Good. So there we go. We've shown the 3 requirements, so we can conclude at the end there. Thus, R is an equivalence relation on X. Hey guys, if you are looking for help with learning discrete math or proofs, I know they're tough, then make sure to subscribe, as I'm literally going to be posting every example I have here for free on YouTube to help you learn and understand discrete math proofs. Back to the example. Great. All right. Second question. Let's go back up here. Find its equivalence classes. All right. So this is now a little trickier. What are the equivalence classes? What are the numbers that are equivalent to each other? So, question here. Find the equivalence classes. All right, well, let's play around with this for a minute. Let's see what we get. What I need, if I have x is related to y, that's true if and only if y squared, again, 7 divides y squared minus x squared, which is the same as saying there exists a k in z such that y squared minus x squared is 7k. But then I've got this y squared minus x squared, which you probably recognize. It's a difference of squares. I can factor that. Great. Now, notice that 7 is prime. So the only way that y minus x times y plus x would equal 7 times anything is if, well, let's put it this way. Actually, yeah, let me write that. It's not a bad way to write it. Since 7 divides 7k, it's kind of silly. 7 divides that whole part, y minus x, y plus x. And since 7 is prime, it follows that 7 divides y minus x, or 7 divides y plus x, right? One of those two factors must be a multiple of 7 to get this. All right, so what this becomes is that two numbers are related if either their difference is a multiple of 7 or their sum's a multiple of 7. Great. Well, instantly, inside of 1 to 14, we can pair up numbers that have a difference of a multiple of 7, right? So we can have, for instance, if if I'm looking at 1 to 14, because that's all the numbers I have, what number would go with, I don't know, 14? Well, in the first part anyway, the difference. The answer is nothing, because 14 minus nothing is never a multiple of 7. The only place it would be is if it's 0 or 7. Okay, I missed one. So if I take 14, take away 7, well, that gives me a multiple of 7. Oh, okay. Well, then what that tells me is 7 is related to 14, right? And if I do this now with 13, what can I subtract from 13 to get a multiple of 7? Well, that'd be 6. What about 12? That'd be 5. What about, keep going down, 11, 10, 9, 8. 11 minus 4, 10 minus 3, 9 minus 2, 8 minus 1. Those are all 7. And so we have that 13 is related to 6. We have that 12 is related to 5. We have that 11 is related to 4. We have that 10 is related to 3. We have that 9 is related to 2. And we have that 8 is related to 1. Okay, we've gotten a whole bunch of relationships right there. All right, so now the only question then is, oh, sorry, do we keep going? Well, if I get down to the number 7, what would I have to subtract from it? 0, and 0 is not in the set X. There is no 0. So I don't get 7 is related to anything this way except for 14. It was related to 14. Okay. And by the way, don't get confused here. I wrote 7 related to 14, and then I wrote 13 related to 6. I switched the order there. It doesn't matter, remember, because it's symmetric. Right? That's the definition of symmetric. 7 is related to 14, or 14 is related, and 14 is related to 7. 13 is related to 6, and 6 is related to 13, and so on. Okay? Now, the only difference then is now I'm trying to look at equivalence classes. So, great, I found that 7 and 14 are in the same equivalence class. 13 and 6 are in the same equivalence class. 12 and 5 are. 11 and 4 are. Do any of these numbers, are they any of them in the same equivalence class as something else? And the answer is no, not from this, but yes from this one. Because now I need to check what numbers add to a multiple of 7. So for instance, if I start with that 1, what else is 1 related to? 1 plus something should be a multiple of 7. Well, if I take 1 plus 6, I get a multiple of 7. Right? But if I also take 1 plus, is there any other numbers from 1 to 14? Sure, 1 plus 13. I also get a multiple of 7. But wait a minute. That tells me then that 1 is related to 13 and 1 is related to 6. If 1's related to 8, 1 is also related to 6, and 6 is related to 13. Look at that. And then therefore 6 is related to 8, and 8 is related to 1, and 1 is related to 13, and 8 is related to 6. They're all related to each other. And so we get an entire equivalence class of 1, let me put them in order, 1, 6, 8, 13 are all related to each other. Now, that one might be bigger. Let's keep going and we'll see what else happens here, right? Let me just erase a few things here. Erase some of these arrows. Okay. So let's keep going. Let's take a look at the number 2. What is 2 related to? Well, 2 plus something needs to be a multiple of 7. So 2 plus 5 would be 7. Well, that tells me that 2 is related to 5. Is 2 plus anything else a multiple of 7? Well, that's the only thing that gets 7. Can I get to 14? Well, I would need 2 plus 12. Oh, look at that. Therefore, 2 is related to 12. And look at what happens. 2 is related to 5, which is also related to 12. 12 is related to 9. 9 is related to 2. 2 is related to 12. 5 is related to 9. They're all related to each other. And so we get another equivalence class here. Again, let's put them in order. 2, 5, 9, 12. Okay, let's erase a few things again. Let's keep going. Now let's take a look at the number 3. 3 plus what would be 7? Well, 3 plus 4 would be 7. Or 3 plus 11 would be 14. Either way, so that tells me that 3 is related to 4 and 3 is related to 11. Well, look at that. 3 is related to 4. 4 is related to 11. 3 is related to 11. 11 is related to 1. They're all related to each other. We get another equivalence class. 1, 3. Oops, that's not a 1. That's a 10. So we got 3, 4, 10, and 11 all together as an equivalence class. Keep going. Almost done. Let's check number 4. Well, wait a minute. 4? 4 plus what's 7? We did that. 4 is related to 3. Well, let's check number 5 then. What about 5? 5 plus 2. Oh, we did that too. So what have we checked here? 1, 2, 3, 4, 5, 6, 7. Where's 7? Up here. Get rid of those lines. 7 up here. All right, so 7's related to 14. Great. Is 7 related to anything else? So we got 7's related to 14 because 14 minus 7 is a multiple of 7. But what about plus? Can I take 7 plus anything else to get a multiple of 7? Well, only another 7. That's it. So 14 minus 7 is 7. And 7 plus 7 is 7. 14 plus 14 is a multiple of 7. 7 plus 14 is a multiple of 7. So the only thing 7 and 14 are related to is each other. And so what we have is 4 equivalence classes, and the last one is just 7 and 14. Now, we normally call an equivalence class based on the smallest number in it. So this would be the equivalence class of 1. This would be the equivalence class of 2. This would be the equivalence class of 3, which is the same as the equivalence class of 4, which is the same as the equivalence class of 10, which is the same as the equivalence class of 11, right? Those are all the same. And this would be the equivalence class of 7. And so we have 4 equivalence classes. Let's just scroll down a bit here. Thus, there are 4 equivalence classes, and they are 1, 2, 3, and 7. And that finishes it off. Scroll down so you can see that there. There you go. Thanks so much. Hopefully you found that useful. Have a good one. We'll talk to you again. Hey, thanks for watching. Remember, what I've explained here is just a tiny, tiny example in the literally infinite space of problems there could be that you'd run into. So, if you're interested in really understanding this content, getting a good grade because you understand the content, go ahead and click the first link down below and book a free call with me, and let's talk about if I can actually help you do well in this course.